Okay, so I'm going to start off with the first question here, and it's on DRAM refresh utilization. And so we start off with this large paragraph here that describes the system that we're going to deal with. So let's go through that. So here we see that the system has 4 channels, and so I'm just going to write this configuration up here so that we have that a little bit summarized. So we have 4 channels, and each channel has 2 ranks, right? So that's 2 ranks of DRAM chips, right? And so each memory channel is controlled by a separate memory controller. Okay, so that means we have 4 memory controllers, right? And so each rank contains 8 banks. So we have 8 banks. And then a bank contains 32K rows. So we have 32K rows. And each row in one bank is 8 kilobytes, right? So we have 8 kilobytes. Okay, and so then we start talking about, retention time and stuff. But this is our configuration. And so I'm just going to here quickly enumerate the values here of how many of each of these we have in the system, right? Because we're going to use that throughout the rest of the question. And so if I quickly make a table of these, right? So let's say the number of these that we have total, not total actually, let's just convert these to powers of 2 first, because we're going to have to do a bunch of calculations with these. So this means we have 2 to the 2 channels, we have 2 to the 1 ranks, we have 2 to the 3 banks. 32K here would be 2 to the 15. 2 to the 15 rows, and then we have 8 kilobytes of data per row, which then is 2 to the 13 bytes, basically, per each of these, right? And so if we now try to ask how many of these total we have in the system, that's basically just, evaluating these multiplied down. So we have 2 to the 2 channels total in the system, and then that means we have 2 to the 1 plus 2, so 2 to the 3 ranks in the system. And then 3 plus 3, right? 2 to the 6 banks, and then 6 plus 15, so 2 to the 21 rows, and then 13 plus 21, so that's 2 to the 34 bytes in the entire device, right? And so in the entire system, rather. And so, 2 to the 34, I guess here is, like 16 gigabytes, right? So that's how large our system is. And so this is a system we're dealing with. Right, so now the question tells us that the minimum retention time among all the rows is 64 milliseconds. And so to ensure that no data is lost, every row is refreshed. So every row is refreshed once per 64 milliseconds, right? And this is done by initiating a command from the memory controller, which occupies the command bus for 5 nanoseconds and an associated bank for 40 nanoseconds, right? So for each refresh operation. And so we're going to consider a 1.024 second span of time. Okay. And so here there's a definition. So we define utilization of a resource such as a bus or a bank as the fraction of total time for which the resource is occupied by a refresh command, right? Which is sort of the natural definition of utilization, right? Like how much, what proportion of time it's used. And so for all of these calculations, we can leave our answer in simplified form in terms of powers of 2 and powers of 10 and so forth. So we don't have to go do unnecessary math and waste time with that. So let's get to the first part of the question. So it asks us how many refresh commands are performed by the memory controllers during the 1.024 second period across all 4 memory channels, right? And so we know here that every DRAM row is refreshed every 64 milliseconds, right? So now if we're considering a 1.024 second period, then how many of these 64 millisecond refreshes, 64 millisecond periods are in this 1.024, right? So that's the first part. And so we have 1.024 seconds is, 1024 milliseconds. So we have 2 to the 10 milliseconds, and we're going to divide by 64 milliseconds, which is 2 to the 6, right? And so we have, this is a 2 to the 6 milliseconds as well. And so we end up with 2 to the 4 of these periods, right? So there's 16 refresh periods throughout this interval. And for each period, we refresh all of the DRAM rows, right? And so up here, we computed how many rows there are in the system because we're considering across all 4 channels. That's this value here, right? So our answer here is 2 to the 21 times 2 to the 4, right? Because every period, we're refreshing all 2 to the 21 rows, and we have 2 to the 4 refresh periods. And so it's actually fine to just leave our answer like that. Or, if we want, we can simplify to the 2 to the 25 and leave it like this. But the answer is correct in either form, right? So the second part asks, what command bus utilization across all the memory channels is directly caused by DRAM refreshes, right? So here, what we know from the first part is that we have 2 to the 25 refreshes in the entire system per 1024 milliseconds, right? Yeah, okay, yeah, it's clear. Yeah, so this is what we've sort of computed for the first part. And so now we're asking about the command bus utilization, right? So remember from before that we have 4 different memory controllers, right? Because each memory channel is controlled by a separate memory controller. And so 2 to the 2 channels means also 2 to the 2 controllers, right? And so if this is 2 to the 25 refreshes for the whole system, there's 1 channel per memory controller. And so the total number of refreshes there, we actually have to divide by the total number of controllers. So we're going to multiply by 1 over 2 to the 2. And so 2 to the 25 over 2 to the 2 represents how many refreshes happen per channel, right? And so this is essentially the number of refreshes per channel over the 1024 millisecond period. And we want to know the utilization across that period, right? And so this information over here told us that every time a refresh operation happens, the command bus is occupied for 5 nanoseconds, right? So we have, so if the time units are down here, we have 5 nanoseconds for every single refresh command, right? And so the time units here cancel each other, right? So we have time and time, and this is number of refreshes. And so this is a unitless quantity, which is what we're expecting. And so then we can just leave our answer like this. We can leave it as 2 to the 25 times 5 nanoseconds over 1024 milliseconds times 2 to the 2, right? And so that's the answer to that part. And like you could go ahead and simplify if you wanted to. You could divide these powers of 2 and convert the time units to the same quantity, but it's correct as is. So the next part of the question asks what data bus utilization across all of these memory controllers, memory channels. It's directly caused by the DRAM refreshes, right? And so if we're asking about data bus utilization, then over here, every time we do a refresh operation, we're not exchanging any data, right? So trivially there, the answer is just 0, right? Because there's nothing happening on the data bus whatsoever. And the last part asks for what bank utilization on average across all banks is directly caused by DRAM refreshes. So how we approach this part of the question is very similar to the part B, right, where we asked about the command bus utilization. Except here we have, so here we had 4 different memory channels, and so we were trying to figure out the number of refreshes per channel, right? And here, if we're asking about banks, we want to figure out the number of refreshes per bank, right? And so we can start off with our same ratio because this is what's happening in the system. So we have 2 to the 25 refreshes per 1024 milliseconds. And so if we're asking about per bank, here we figured out that there are 2 to the 6 banks in the entire system, right? So we want to divide this number by 2 to the 6. And so this is the number of refreshes that go to a particular bank in this time period. And so in terms of the utilization, over here, the information told us that a bank is busy for 40 nanoseconds per refresh command. So here the scale factor was 5 nanoseconds. Over here, the scale factor will be 40 nanoseconds, right? So 40 nanoseconds per refresh. And so the computation is like exactly analogous to that, just with different values, right? So here we have 2 to the 25 times 40 nanoseconds over 1024 milliseconds times 2 to the 6. Right? And so this is the utilization. If you go ahead and evaluate these, I think the values are in the solutions we have online. Right? This is about 4%, and this is about 2%, right? And so if you did go ahead and compute that, that's what you would end up with. Okay, so are there any questions about that part so far? I'll move on to the next thing. Yeah, okay. So the next part of the question asks us to optimize this a little bit, right? So there's more text here. And so the system designer wants to reduce the overhead in order to improve system performance and reduce energy. Okay. So what we observe is that not all rows in the DRAM chip need to be refreshed every 64 milliseconds. And in fact, we only need to refresh some rows at lower values, which are indicated in this table, right? And so this table provides us with what we need. So there's 3 different refresh rates here, 64 milliseconds, 128, 256. And we have a different number of rows that fall into each of these buckets, right? 2 to the 5, 2 to the 9, and all other rows. And the question then asks us that given this distribution, if we only refresh all rows as necessary, how many refreshes are performed by all the memory controllers during the same time period across all 4 channels, right? So it's basically the same thing this guy asked for, except now we have different refresh rates. And then after that, we're asked about the command bus utilization, and then here, data bus utilization, bank utilization. So it's the same sort of computations we're going to do, right? Except here we have a different number of rows. So we started off here by defining how many of these 64 millisecond refresh periods were in the interval we're considering, right? And so it ended up being 2 to the 4. So we can do the same thing here and sort of, for each of these different refresh rates, compute the number of refresh intervals in a 1024 millisecond period. And so for 64 milliseconds, it's the same, right? There's 2 to the 4 of them. For 128, it's 2 to the 3, and for 256, it's 2 to the 2. And then the number of rows that are refreshed in each period, so we have 2 to the 5, 2 to the 9, and then all other rows. And so to figure out what that value is, we know the total number of rows in the system, which was 2 to the 21. And so we can simply write this as 2 to the 21 minus the rows that are specified, right? So minus 2 to the 9 minus 2 to the 5. And so now we have all these quantities. And so figuring out how many refreshes are necessary during this period is just multiplying those values through, right? It's nothing too complicated. So we have 2 to the 4 rows that we have 2 to the 5 rows that need to be refreshed 2 to the 4 times. So over there. And then we have 2 to the 9 rows that need to be refreshed 2 to the 3 times. And then we have this quantity of rows here, 2 to the 21 minus 2 to the 9 minus 2 to the 5. That needs to be refreshed 2 to the 2 times, right? And so that's the answer. And so again, we can leave it like this or simplify if we want to, right? Okay. So the next part is the command bus utilization. And so this computation is basically exactly the same as we do up here, right? Except instead of 2 to the 25 refreshes per channel, we essentially have a different value. And so instead of writing this repeatedly, I'm just going to define this as a variable n, right? Because it just makes this a little bit easier. And so what we have here is that we have n refresh operations happening per 1024 milliseconds, right? Where we computed n in this part. And so we basically do the exact same thing as up here, right? So we have n refreshes total in the system, but we know that we have 4 different memory controllers and therefore 4 different channels. So we have to scale this by 4. So we essentially divide n by 2 to the 2, right? And so that's the number of refreshes per channel. And it's happening over this time period. And we know that each single refresh operation keeps the command bus busy for 5 nanoseconds, right? So 5 nanoseconds per one refresh. And so the answer then is just n times 5 nanoseconds over 1024 milliseconds times 2 to the 2, right? And once again, you could go ahead and simplify it. Based on the solutions, this ends up being like about 1%. It's not something like that. Yes?
So you consider that this command bus utilization is for
Yeah. Right, so each channel experiences the exact same number of refreshes, right? Because there's the same number of rows. So, okay.
So you said up there that those are different intervals for different numbers of rows?
Yes.
But in the whole system?
Yeah. Okay. Yes, absolutely. That's a very good point. And so here what I computed was assuming that these are uniformly distributed across the 4 channels, right? I guess I made that assumption without it being stated. Yeah, I think you need to make that assumption. And so if in a say an exam situation you thought about that, you could just write it here, like I'm assuming that whatever. And if you write that as we're grading, like as long as that assumption is reasonable and your answer makes sense based on the assumptions you made, that should be fine, right? Yeah. Okay. Is that fair? Yeah. Okay. Go ahead.
Can you, in an exam situation, leave your answers in terms of n or like an expression, or do you need to calculate it like you did at 1%?
No, that's right. So you don't have to do this 1% part. This was fine for homework because you could just plug this into like, calculator or whatever. In your exam, it's okay to leave it like this as long as it's clearly defined what you're doing. So here n, I very explicitly defined here. This is what I'm referring to, right? And so I think it's very clear when we're grading your exam that that's what you meant. If you do something strange or it's really hard to read, then it might get confusing for us to grade, and then you might lose points, and then it'll be a mess. But yeah, just be clear about it, and your expression should make sense, right? So I think here, writing it out like this, while it's not in the most simplified form, it's clear what you were computing. And so even if one of these values was wrong, right? Let's say you accidentally wrote 2 to the 6 here. Fine. It's still like your methodology is correct, and you'll get the partial credit that you deserve because you did the right thing. You just screwed up one value or something. Yeah. Okay. But yeah, you had a question? I see. Are you saying that it was specified as bank here, or that it's ambiguous? Yes. Oh, I see. And so you're saying you can interpret this table either way based on that information? Yeah, sure. I think that's fine. And then just write it as your assumption. Does it? I mean, you just recompute your number of rows based on that information, right? Because if you assume each bank has this exact same ratio, then each channel will have the same number of refresh commands happening. So it wouldn't be ambiguous in this case. You just end up with a different value based on the number of rows. Yeah, it would just essentially balance the ratio towards these guys, right? So instead of this being, 2 to the 4 times 2 to the 6, it would be, all this done at a bank scale. And so you'd have a different ratio of each. I think that's fine. If the question allows you to interpret it that way, then yeah, just state what you did. Yeah. Right. Is that fair? Okay. Yeah, are there any other questions? Okay, then I'll move on to the next part. Oh yeah, so we're still continuing this part, sorry. So here, can you see everything? Okay, yeah, sorry, I guess I'm sort of blocking that for some of you. I'll put it up here for now. So it's asking us the DRAM data bus utilization. And same as the first part, right? We're not utilizing the data bus, so this is easily just 0. And so then this asks us what the bank utilization is on average. And so again, here we can treat it kind of the same way we treated it for this part, right? And basically the same we're doing here, except it's just a different factor. And if you're making a different set of assumptions, then I guess you might do this a little bit differently. But the process should be the same, right? So here we had n refresh operations for the entire system per 1024 milliseconds, right? And so here we want to divide n by the number of banks in the system because we're assuming that it's equally divided among banks now, which is, I guess, the assumption that you stated, right? So, so here we have 2 to the 6 banks in the system. And so we're going to say that these refresh operations are equally distributed amongst banks, right? And so that's how we would arrive at this answer. And yeah, it's 40 nanoseconds per refresh operation. And so when we compute that, it's n times 40 nanoseconds over 1024 milliseconds times 2 to the 6, right? And yeah, I think, yeah, in the solutions, that's like about 0.5%. But yeah, so does that make sense? I think it's basically the same computation you did before. So now part H is asking that now we want to achieve this reduction refresh by refreshing rows less frequently. So in order to implement this improvement, the system needs to track every row's required refresh rate, right? And so what's the minimum number of bits required to track this information? So, okay, so we need to track every row's required refresh rate, right? And so here are the refresh rates we're dealing with. And so there's exactly 3 refresh rates, which means there's 3 different states that we need to be able to identify for each row, right? And we know that there's 2 to the 21 rows, right? So we have 2 to the 21 rows times the number of bits to encode three states, right? And so that would be, sorry, yes?
I actually wrote an email about this.
Okay.
Because, yeah, you can use 2 bits to encode 3 states, but if you consider more rows, you can, for instance, use 5 bits to encode all the combinations of 3 rows. So,
right.
Really, you would have to multiply by log of base 2 of 3.
Yeah, I was actually about to write that exactly. Yeah. No, I mean, you're right. So there are different ways to do this, right?
It's just that it explicitly says
yes.
minimum number of bits. So
yeah. So you went ahead and found a more optimal scheme.
Well, it's actually then optimal. You could not encode the information in fewer bits than that. I mean, no matter how you implement the algorithm for it,
right?
It's like
okay.
And question about information, you can
Yeah, so you found basically the information theoretic bound for encoding all the information that you need to encode, right? That's what happened there. Yeah, I think that's perfectly acceptable as long as the question allows that interpretation, right? So yeah, as you said, this asks for the minimum number of bits of storage to track this required information, and I think the quantity you computed satisfies that criteria. Yeah, I think so. This question leads you towards tracking each row state individually, right? So that's what this would be, right? 2 to the 21 times 2 to the 1, which is, I guess, the solution that's stated in posted on the online solutions. Okay, fair. Yeah. So then part I. So this question asks to assume that the system designer now implements an approximate mechanism to reduce the refresh rate with Bloom filters. And so one Bloom filter represents all rows with 64 milliseconds, another one for all rows which require 128 milliseconds. And so we go ahead and modify the memory controller's refresh logic. So on every potential refresh of a row, so every, say, 64 milliseconds, it probes both Bloom filters, right? So both are probed for every potential refresh of a row. And so if either of the Bloom filters results in a hit, and if the row has not been refreshed in the most recent length of time for the refresh rate associated with that Bloom filter, then the row gets refreshed, right? And so if a row address hits in both, the more frequent refresh rate wins, right? So the 64 millisecond Bloom filter has priority, essentially. And so any row that does not hit in either Bloom filter is refreshed at the default rate of per 256 milliseconds, right? So we have a Bloom filter for 64 milliseconds, a Bloom filter for 128 milliseconds, and I guess the default of 256 milliseconds, right? And so we probe these two where the 64 millisecond has priority, and if neither of them are a hit, then we use the 256 millisecond quantity. So here we're provided with the false positive rates for the two Bloom filters, right? And the false positive rate is essentially if we query the Bloom filter with a particular address, what's the probability that it will tell us, that it's in that bin, even though it's not, right? And so we're saying that the distribution of row refreshes specified in part E still applies. So this table here is the same set of values that we're going to use for this part of the question. And so now it asks us to repeat the same computations, essentially, right? How many refreshes are performed during the 1024 second period across all four memory channels? So what we have is essentially we have these values, but we're also going to rearrange these bins a little bit based on the false positive rates, right? So for the 64 millisecond bin, we have 64 millisecond bin, and we have 2 to the 5 rows that are guaranteed to hit in the Bloom filter, right? So these 2 to the 5 rows they're true positives, essentially, right? And so we have 2 to the 5 plus the false positives, where the false positives will be essentially described by this 2 to the minus 20 quantity, right? So the probability that an address will, become a false positive is 2 to the minus 20. So we have 2 to the minus 20 times the total number of rows in the system, right? And so the total number of rows is 2 to the 21. So that is actually just 2 to the 5 plus 2, right? 2 to the 1. And so this is the number of rows that'll end up having 64 millisecond refresh because of the false positive rate. So now we consider the 128 millisecond bin. And so in the 128 millisecond bin, we have 2 to the 9 rows. We have 2 to the 9 rows, right, that fall into this bin. And then we have a different false positive rate. So we're going to have 2 to the minus 8 times 2 to the 21, which is 2 to the 9 plus 2 to the 13, right? 2 to the 13 rows. And so those will be essentially everything that's refreshed at 128 milliseconds. And then we have 256 milliseconds, which is everything else, right? And so we compute the everything else in the same way, so as we did before, right? So we have 2 to the 21 rows total, and then we just subtract these quantities, right? Minus 2 to the 9, minus 2 to the 13, minus 2 to the 5, minus 2 to the 1. Yeah? And so now we're going to go ahead and just sort of do the same thing as before, except now instead of these values as a number of rows, we have these values. And again, for simplicity, I'm going to clearly define here that this is going to be called N64, this is going to be called N128, and this is going to be called N256, right? Just to save some time here. And so we compute the number of refreshes here using the same values as here, right? So we essentially have N64 rows that get refreshed 2 to the 4 times, N128 2 to the 3 times, and N256 2 to the 2 times, right? So we just write that here. We have N64 times 2 to the 4 plus N128 times 2 to the 3 plus N256 times 2 to the 2. Yeah? So that's all that is. It's just computing a different number of rows. So then what command bus utilization results from this refresh scheme, right? So same analogous computations as before, right? So we have this quantity, which I'm going to define here, let's say as M, right? All of this stuff. And so we have M refreshes per 1024 milliseconds, right? And again, it's the same thing, right? Command bus, so we have 4 channels in the system, and then we have 5 nanoseconds per refresh, and so we end up with M times 5 nanoseconds over 1024 milliseconds times 2 to the 2, For data bus utilization, again, we don't touch the data bus for this scheme, so it's still 0. And for bank utilization, same sort of thing as before, right? We have M operations per 1024 milliseconds times, so here we have 2 to the 6 banks times 40 nanoseconds per refresh operation. So M times 40 nanoseconds over 1024 milliseconds times 2 to the 6, right? And so that's essentially the last part of the question. And all the comments that you guys have made throughout also apply to this part, right? So here I'm making the same assumptions that the rows are uniformly distributed throughout all these different channels. And yeah, these are probabilistic arguments, right? Because depending on exactly which rows fell into here, they could potentially not be in the 128 bin, right? Because if these two were selected from the 2 to the 9 pool, this would actually be 2 to the 9 minus 2, right? So I'm just doing this as a general probabilistic argument, and this is fine because it's essentially, it would change very little if you were trying to compute these values. But yeah, so I think if you're ever in doubt, just state exactly what your assumptions are. And if those are reasonable assumptions and the question allows that interpretation, it should be good. Yeah. Okay, so any other questions about this? Or no? Yes. Yeah. You're saying it's that quantity, right? False positives over true negatives, as opposed to false positives over the sum of all different possibilities. Yeah. So, yeah, I think in the context of Bloom filters, we've been talking about it like this in terms of the lecture slides and in this course, essentially. So this interpretation is sort of what I just assumed. Yeah, if this is going to be your sort of pedantic interpretation of false positive rate and you state that clearly and then solve according to that, sure, that should be fine. But we would much prefer if you use the definition we've used in the course, right? So that's what this exam is supposed to cover. Okay. Okay, sounds good. Cool. So then I'm going to pass it off to Hassan, who's going to solve the next question for you guys.
Okay. The next question is from the second homework. This is question 5 from homework 2. Okay, so it covers caching and processing in memory. And the question is like this. So it defines 2 arrays, 2 integer arrays, A and B. And they have elements of size 4 bytes. And here you can see the base addresses of A and the base address of B. And here we have a piece of assembly code. So I won't go through this code now, but instead I will directly jump to the question. I think it will be easier if you do so too, because first trying to understand the code might be more difficult if you don't know what to answer. Okay, it makes more sense to first read the question. So here it further says that we have a single core processor that executes this code, and this processor does not have any caches. The load store instructions access directly the main memory, and then we have a fixed latency of 50 cycles for both read and write operations, and those are serialized. So it's pretty easy so far, right? Everything is serial. We have fixed latency, no cache, and memory requests cannot be overlapped. Okay, so everything is pretty straightforward, and then the execution time of non-memory access instructions is 0. So here in this code, we will take into account only memory accesses. Okay, and then the question is, what's the execution time of this piece of code on this processor without any caches and 50-cycle main memory latency? So now if you look at the code, we see that we have 2 loops named outer loop and inner loop. And if you check here, what is the condition for the branching against the inner loop? It is basically this, this case where R4, register 4 is not equal to 2. So here we set R4 to 0 at the beginning of the outer loop, and here we increment it, right? Anywhere else in the code, we don't modify R4. So basically, this will mean the inner loop will execute once. At the end of the first iteration, we will increment R4, and here we will compare 1 against 2. And since 1 is not equal to 2, we will need to repeat the inner loop one more time and then exit. Okay, so the inner loop will execute 2 times, and then the outer loop will execute how many times? So here it will branch on R3 equals 16, and then we increment R3 here, and we set R3 at the beginning of the program. So this basically means the outer loop will iterate 16 times, and in each outer loop iteration, we will do the inner loop twice. Okay, in total, we have 32 inner loop iterations. Okay, so inside the inner loop, we have 2 loads. Let me use a different color here. So we have 2 loads. And at the end of the outer loop, we have a store here. Since we execute this twice, the inner loop twice, we'll have 2 loads. 2 loads per iteration and 4 loads per outer loop iteration, and then followed by 1 store. And then we will repeat those 5 memory accesses 16 times. Okay, and then the answer of this first part is pretty easy, right? So we have 16 outer loop iterations. We do 5 accesses, and each access takes 50 nanoseconds. And then if you do the math here, it's basically, this is cycles, not nanoseconds. And the answer will be 4,000 cycles. Okay, this part is pretty easy, right? Any questions on this? Okay, so now it becomes a bit more complicated because we add a 128-byte private cache. And here are the properties of this cache. So the cache block size is 8 bytes. Okay, so based on this information, we can directly see that we can fit 2 elements, right, into one cache block. This is important. And then the cache is direct mapped. And access to the cache takes 5 cycles. And on a miss, we go to the main memory and then again pay the 50 cycle latency. And the question is the same. So if you have this cache, what will be the execution time of this code here? Okay, so this part is a bit more tricky. First, we need to understand exactly where in this cache elements of A and B will map. So we know that the cache is direct mapped, and it has 128-byte capacity in total, and each cache block is 8 bytes. So basically, here we'll have 16 entries that are direct mapped, right? So I find it basically by dividing 128 by 8. So it will look something like this. So this is the first set or entry, and then second and third, we have this until 15, right? So then if we look at the base addresses here to determine where in this cache the first elements of A and B will map, so we can first basically find out which bits of the address tells us the entry in the cache to access, right? And then since we have 128 bytes here, the last 8 bits of the address will have to do something with the cache, right? So basically, since we have 8-byte blocks, the last 3 bits of the address will be the offset, right? So which byte within the cache block is addressed. So like those 3 bits, least significant 3 bits will indicate that. And then, this is 4. And then the next 4 bits here of the address will tell us which entry of the cache that address is targeting. So if we convert this hex number to binary, we will see that we have like a bunch of zeros here. So we'll have 12 zeros, and then here we'll have 1. Right? So we can easily see that here the first element of address A will go to the first entry of the cache, because all least significant 7 bits are 0. And so it's the same for B, for the base address B. Again, here we have 12 zeros, right? So this basically tells us that the first elements of A and B will conflict on the first cache line, on the first entry over here. So basically, when we access A0, when we want to access A0, it will bring A0 and A1 to this position. And then if we want to access B0, it will evict A0 and then put B0 and B1. Okay? So based on this, we can now start understanding what this access pattern looks like. So here in this code, we see that R1 is the base address of A, and then R2 is base address of B. So this first load is targeting some element of A, and then the second one is targeting an element of B. So here we use R5 to iterate over this array, and here we use R4. So R5 is calculated by adding R3 and R4. So we already have some understanding about R3 and R4. R4 is basically the counter that we modify inside the inner loop, right? So it gets either 0 or 1 as a value. And then R3 is the outer loop iterator, which gets values from 0 up to 15. And so basically what will happen here is we will first access A0, right? Because initially R5 will be 0 plus 0. And then in the next iteration of the inner loop, we'll access A1. And for B, we'll access B0 and then B1. So those will be the locations we will touch in the first 2 iterations of the inner loop. And then here for the store, it is R1 plus R3. And R3 is our outer loop iterator. So it will be basically the base address of A plus R3, which initially will be A0. Okay, and in the next iteration, what will happen is we first, after we complete the first outer loop iteration, we will go back here, we will reset R4 to 0, and then we will calculate R5 as 1, because we incremented the outer loop iterator plus 0, so we'll have 1 here, and then we'll access A1 first, and then we'll access A2. Okay, but for B, nothing changed. We'll again access the first element of B, B0, and then B1. Is that clear? So basically it goes like this. A0, or let me put it that way. So we touch 0, element 0 of A, and then 1, and then 1 again, and then 2, and then 2 and 3. It goes this way. But for B, we basically repeatedly access elements 1 and 0 and 1. Okay, so here it's not only important to determine exactly which locations we access, but also the order of those accesses is important because they are conflicting in the cache. So in addition to compulsory misses that we'll have, we will also have conflict misses in the cache, right? And let me show that too. Okay, so in the first outer loop iteration, those will be the addresses that we will access, right? So we will first access A0, and then we'll access B0, and then A1, and then B1. And then finally, we'll do A0 again to store the value that we calculate. So initially, the cache is empty. We will we'll get a cache miss. So this is a compulsory miss for A0. And then same for B0. This is the first time we access B0. But here, an important point is that when we access B0, it will evict A0 because they map to the same cache entry. Right? Okay. And then we access A1 again. So A1 was brought by when accessing A0 because they map to the same cache block, right? So we sort of prefetch it. But since B0 evicts that block, at this point we will not have A1 in cache. But if we didn't have this access to B0 here, then in that case, the second access would have been a hit. Okay, and then here the same thing happens. A1 discards B0 and B1 from the cache, and then we get another miss here. And then the same thing happens, and then we again get a miss. So this is what happens in the first iteration. All accesses miss in the cache. And the second outer loop iteration, so as I said, we increment A in each iteration, but we keep accesses to be the same. Okay. And then now, so the last element we accessed was A0, which brought A0 and A1 to the first cache line. So this is a hit, right? And then B0, access to B0 again, this is not in the cache, was evicted, and this discards A1 and A0. So then we access A2, so this is the first time we touch that cache block, so this will be compulsory miss. And then B1 is in the cache because A2 maps to the next entry, right? So A2 will be placed here together with A3. So B0 will remain in the first cache line. So we'll have a hit here. And then since A1 is not in the first cache line, we'll get a miss. Okay. Nice. Okay, I'm going to now quickly go through some other iterations just to show you the hit and miss pattern that we'll eventually get. So A3, B1, A2. So in this iteration, what will happen is we already have A2 in the cache. Nobody evicted it. This is a hit. Do we have B0? No, because last time we accessed A1, which evicted B0. This is a miss. This is a hit. A3 came together with A2. And then this is a hit because B0 brought the cache line. And then A2 is hit again. Okay, so this is what happens in the third iteration. And I think I'm going to show 2 more iterations. A4, B1, A3. We accessed A3 before. This is a hit. We have still B0 in the cache. So if it's difficult for you to follow what's in the cache, what's not in the cache, you can use this and then basically write it here, what is currently in the cache, and then when you evict something, you can just modify it. But I'm not doing it just because I like to save some time. But in the exam, if you think you can make a mistake, you can do it more safely. Okay, A4 is a new cache block that we'll need to access. So here we'll have a miss, and then for B1 we'll have a hit. And for A3, we will have a hit. So here, at this point, you see that starting with this third iteration, actually, we always get, starting with this iteration, we'll always get hits for elements of B. Because they won't be evicted, we don't access A1 and A0 in those iterations. And we will also get always hit for A3, because we will first access it here in the beginning of the iteration, and then B won't conflict with it. And every second iteration, we will get a miss on this element here. So let me execute one more iteration. So here we will do access to A4, B0, A5, B1, and A4. So what will happen in this case is we already have A4 in the cache, so this will be a hit, this will be a hit, this will be a hit because A5 came with A4, this will be a hit, and this is also a hit. Okay, and in the next iteration, we will basically have hit to A5, hit to B0, miss to A6, it's a new cache line, and then hit again, hit again. Okay, so starting from this, starting from this iteration here, we will have 1 miss and 0 misses, right? And those will interleave. 1 miss, 0 miss. We know that in total we have 16 iterations, so we will end with what? With 1 miss, right? Here. And here we have 1 miss for this iteration, 3 misses, and 5 misses. So if we add everything together, it is 8 misses here, 8 misses plus how many? So it's 13, divided by 6, 7, right? So we'll have 7 more misses here. Sorry? 13? Yeah, it's 7, isn't it? Oh, yeah, okay. Sorry. This is 9. Okay. I was like, okay. Yeah, so in total we have 16 miss. And then the rest will be hit. So like it's quite easy to calculate how many accesses we have here in total, right? So it's like 16 multiplied by 5. We have 80 accesses in total. 16 of them will be misses, and the rest is hits, right? We have 64 hits and 16 misses. So based on that, you just do the math. You have the number for, so it takes 5 cycles to serve a request from the cache and 50 cycles otherwise. You do the math, and then you end up with the execution time. Okay? Yeah. Yeah. Yeah, so I think, so I don't remember what we did in the question, but it's not like very explicitly stated what happens exactly, but in the question, so it says, on a miss, the main memory is accessed, and the access fills an 8-byte cache line in 50 cycles. So that will mean you should also apply another 5 cycles to bring the data from the cache to the processor, right? So it should be 55 cycles in total for a miss. So what we used here is so here in the solution, apparently we don't take that into account, so we just use 50. I mean, ideally this should be clearly specified in the exam question, okay? So it will be like all the way to the CPU, you bring the data from the main memory in X cycles, or you bring it only to the cache in X cycles, and then you still have to pay the hit latency. Okay, it will be stated clearly in the exam. Okay, so that was part B. Any other questions? Yes.
I think this is outside the scope of this problem, but for like store instructions, normally we have to consider like the write group of loading information to the cache.
Right.
We're just treating it as the same as
Yeah, exactly. Yeah, here it's very simple in this question. Yes. Okay. I had a blank page here to use, but yes.
But here you're assuming that the memory is word addressable.
No, it's byte addressable.
But if you see in the code, for example, if you assume R2 is 1 and R4 is 8,000, the address will be 8001. Whereas to access B of
Oh, okay.
So yeah, it's
Okay, yeah. So here, we also have a mistake in the code, I think. Yeah, I agree with that. So here we should increment with,
this is different. If you
not by 1, by 4, basically.
yeah.
Yeah. Okay. Okay. Yeah. Like you're asking about like which elements in the code we access?
Many times in the exercises,
Mhm.
I calculate the offsets, and I'm not really sure about what I do.
Like this part here?
Yeah.
Okay. So here, the overall cache size is 128 bytes, right? So this means we'll have 8 bits to determine like where in the cache data will map, right? So like for example here, we know that a cache block has 8 bytes. So that will mean we will need to use 3 bits to determine the position, the byte position in that cache block, right? So you have 8 different bytes. You address 8 with 3 bits.
So you say that we try to address 1 byte.
Yes.
Okay.
Yeah.
How do you know you're trying to address 1 byte?
So if it's not stated otherwise, you should always assume byte addressable memory. So like in lectures, like everything we do is byte addressable. If it's not byte addressable, it will say that in the question. So it's like I think it's sometimes difficult to think about like things that we have to define in the question. So like we usually end up having such issues. Like you can always find something that people like design differently in their systems, but like I don't know any system that use anything else than byte addressing, like in the real systems. And this is also what we use mostly in our questions and in the lectures. It's always byte addressable. Yeah. Yeah. I think so, yeah. As long as what you're doing is reasonable, and if there's like any issue or anything not specified in the question, and then you solve it based on your assumptions and everything is reasonable, I think it's good. Okay.
The offset will be always 3, except if we...
So the least So the least significant bits is basically the offset, right? So typically cache lines are 64 bytes. So in that case, you'll have 8 bits that you use. Sorry, not 8. Yeah, you have 6 bits as an offset in that case.
yeah, sorry.
Yeah. I mean, I don't want to confuse you further, but you can think of it as an address of the byte inside the cache block, right? That's what we call offset. Okay. I will continue with the part C. So here, this part is very similar to the first part, which was very easy, where we had a processor without any caches, and we directly accessed the main memory with 50 cycles. But here instead, it says that we have a near memory processor, which has only 10 cycle access latency to the data in the main memory. And we don't have caches again. So this is exact same computation that we need, calculation we need to do for part A here, except we change 50 with 10. And then you end up with 800 cycles of execution time. Okay, I think that was very easy. And then part D is, so let me read this quickly. Your friend Oh my God, we have too many mistakes in this question. Your friend now suggests that by changing the cache capacity of the single core processor in part B, she could provide as good performance as a system that utilizes memory processing in memory unit. Is she correct? What is the minimum capacity required for the cache? Blah, blah, blah. So here, she's not correct because no matter how big is the cache, no matter how many entries we have here, we will have conflicts in the cache line 0 here, and then it will increase the execution time a lot, so we can never complete the program in 800 cycles, even if the rest of the accesses are always hit. And we also have compulsory misses. So if you do the math, if you try to calculate the best case here, you will see that you cannot do better than this over here. So basically what will happen is by just increasing the cache size, you'll only be able to turn those misses here to hits, right? But you will have the rest of the misses here, which are the compulsory misses. Yeah. Mm-hmm.
Does it say that we cannot increase the size of one block? Then we will only have two misses, right?
Yeah. So here it is just increasing the cache capacity by increasing the number of entries. You cannot increase the cache size by increasing the cache block. So it has like different consequences, right? As you know, because like increasing the cache block size will also need to potentially increase the number of bytes you fetch from the memory for each request, and then you may also need to maintain some metadata to know like which parts of that big cache block you have brought to the cache. So it changes the design completely. So here, in this part, you just change the cache by increasing the number of entries you have in the cache. And in the second part here, or in the fifth part, in part E, it asks you how you can change the cache design while keeping the capacity the same, or like also increasing the capacity potentially, how you can change it to improve the performance of the design with cache. And here the answer will be basically, so what was the problem here with the previous cache design? We had those conflict misses, right? So we have to have a design that will avoid the conflict misses. And the best thing you can do here is just to turn this cache to a design where you have two ways, right? In that case, you can keep both B0, B1, and A0 and 1 together in the cache, and you'll avoid all conflict misses. And you don't have to increase the size of the cache. It's not helping because you don't have temporal locality here, right? You only have temporal locality to elements of B and some elements of A. Actually, you have some, but you don't need a very big cache, right? So only like having a cache with like 16 entries, for example, is like good enough. So you don't have to increase that. Okay. Yeah, I think I agree. That's a different thing you can do to improve performance. So basically, in that case, you will not only turn those conflict misses to hits, but also some of the compulsory misses because you will prefetch the data. Yeah, so this is like sort of a more open-ended answer, basically. So you have like two options at least. You may also come up with some different change in the design to improve performance. So in such cases, you basically have to list everything that you can think about to improve performance or, yeah. Okay, any other questions? Yeah, okay, I agree with that.
And it was so many times that I'm facing a question and I don't really understand that.
Yeah, so as I said, in the final exam, it should be much more clearly defined. Yeah. Okay. Then we will continue with the next question.
Okay, so is it visible? Yeah, okay. Okay, so this question actually talks about the DRAM scheduling and the latency policies. So, okay, let's read the question. So you would like to understand the configuration of the DRAM subsystem of a computer using the reverse engineering techniques. And this is basically the set of knowledge you have from this particular DRAM subsystem. Okay, what are the knowledge? Basically, the physical address, you know that, okay, it's for 16 bits. And the DRAM subsystem consists of a single channel and a 4-bank system. And the DRAM is byte addressable. It's clearly mentioned here. And okay, the most significant 2 bits of the physical memory, it determines the bank. So you know how to decode the physical address to get the bank number. And the DRAM command bus operates at the 500 megahertz frequency. And this point basically says, okay, the memory controller issues a command to the DRAM in such a way that no command for the servicing a later request is issued before issuing a read command for the current request. So that basically says that if you have, let's say, 2 requests, which is a request A and B, and let's say A actually came first, A is the old request, so, and even if A and B are going to the 2 different banks, the memory controller does not issue an activate command to the bank that actually holds B before issuing a read command. So basically you can think of it as like a first come first serve rather than any open row policies, or it's completely oblivious to which bank you are currently, if you have a bank parallelism or not. Make sense? And yeah, and then it basically says that, okay, now you have, this is the state of the memory request that you have currently in the DRAM request buffer. And the third sequence basically says that, okay, at the same time, you take the snapshot of the request buffer and you start probing the DRAM command bus. And you observe the DRAM command type and the cycle at which this command actually issued. And the following are the DRAM commands that you are actually seeing. Make sense? And then the questions are like, okay, so it's actually asked for, let's say, the activate to read latency, activate to pre-charge latency, and the pre-charge to activate latency. So now let's see how we, if we know this kind of information, how we can actually reverse engineer the system and get some data out of it, right? So the first question is it's visible, right? Yeah, okay. The first question is to activate to read latency, right? So, okay. Before start using any kind of questions like this, let's first decode what the information we have currently. So we know how to get the bank information from these addresses. So let's say get the bank numbers first, okay? So this guy actually goes to bank 0100, so that means bank 01. Am I right? Yeah. So 01. So I'm just decoding the first hex digit. So the second one would be 0000. So that means the first 2 digits basically gives you the bank now ID. So that means this goes to bank 0. This one goes to bank 1 again. This one is bank 2. This one is bank 3. This one is bank 2 again. And this one is 1, right? So let's write it in normal form. So this is 1, this is 0, this is 1 again, this is 2, this is 3, this is 2, and this is 1. Right? So we know that which bank this request is going to. Make sense? Okay. Now we want to know, let's say, the activate to read latency. That's the first question. So let's see if we so activate to read latency is bank oblivious. So you have this activate command followed by a read command. That's there. And another pair exists here. Another pair exists here. So this is the first pair. And another pair is here. Right? So basically the activate to read latency is basically saying that you have a 4 cycle of latency. Make sense? So then the answer would be, this would be 4 cycles. Now the latency, so that means you need to convert it to a seconds format. you know that your DRAM command bus operates at 500 megahertz of frequency. That means your cycle is basically of 2 nanoseconds each. So that essentially gives you 8 nanoseconds of activate to read latency. Is it clear? Make sense? Okay. Now the second question is activate to pre-charge latency. Okay. Now let's see. Now activate to pre-charge latency, if you recollect the DRAM operation. So activate to pre-charge latency actually has to do with the DRAM row conflict. Make sense? So if you have a different open row, row open, so you need to actually close that row before opening a new row, right? So let's then focus on the accesses which are going to the same bank. Make sense? So yeah, so let's see. So this is the if we now the read accesses. The reads are the one which is actually happening to the for all of these accesses, right? So if we then simply categorize these accesses like this, so these 3 command sequences are actually happened for this access. Okay, then this command sequence is happened for the second access. Then the third 3 command sequence actually happened for the third access. These 2 is for this read. This read goes independently, this read goes independently, and then these 3 is for the last access. So this is access number 1, this is access number 2, 3, this is 4, 5, 6, and 7. Do we have 7? Yes, we have 7. Okay. So now, So now the question is activate to pre-charge latency. So let's see, the activate to pre-charge. Okay, now if you see, so let's say access 1 and access 3, these 2 accesses are going to the same bank. Make sense? So access 1 and access 3, these 2 are going to the same bank. So you should be actually worrying about the activate to pre-charge latency between these 2 cycle counts. So cycle number 6 and this is cycle number 21. Does that make sense? So that gives us a cycle difference of 15 cycles. 15 cycles translates to 30 nanoseconds. Does that make sense? Okay, yeah. There is a row conflict. So you have, okay, so these 2 accesses are going to the same bank, right? Now, I'm saying these 2 accesses are going to the same bank, but if you look at the access sequence of these 2 accesses, this guy is opening a new row, right? Pre-charge, activate, and read. So, yeah, go ahead. Mm-hmm.
Then that happens independent of the other bank.
That's true. That's true. Yeah. Okay. Okay. Okay.
Like 2 or 3 more requests, this latency would increase.
Sequence of requests is happening, but doesn't it, if you have the accesses to the same bank, it should be like the access to the different bank should not hamper the access sequence on this bank, right?
So if I had like 2 more reads in between.
Okay. Okay.
Request 1, then we have a read request, just a read command for request 2. So if I had like 2 more reads after this request 2,
Okay. Okay.
the request to some different bank, this latency would automatically increase.
Okay. That's true. That's true. Yes. Yeah, that's true. That's true. But in this case, we know that these read requests actually happened in cycle 11, and before cycle 21, you don't have any other request. That's one hint you actually have. And you know that, okay, request number 1 and request number 3 actually went to the same bank, right? And request number 3 actually initiated a sequence which is saying that precharge, activate, and read. Okay.
But right now you said activate to pre-charge.
Yeah, right.
Okay, I will calculate access 3 to access 7. Both go to the same bank.
Oh, okay. I see.
100 cycles.
I see.
That it's actually every activate and read differs by 4 cycles. So there's 6 times.
That's true.
Later on there's 27, 31. So we can be sure that this is
Okay. Yeah, I believe the question you ask is like correct. Yeah, so activate to pre-charge, whenever we are saying that activate to pre-charge latency or let's say activate to read latency, we are actually talking about the minimum time we are thinking here.
So activate to read can be minimum by itself because it's a sequence.
Makes sense. But the activate to pre-charge, it can be longer, right?
Right.
Exactly. So here what we are trying to find is basically the minimum activate to pre-charge latency. Does it make sense? Yeah.
So this question sort of, so like in this example, all the activate to reads are the same length. The homework is one that's shorter, the one that's longer.
Okay.
But normally when we consider latency, don't we care most about what, like typically what takes the longest, because then we can like
Okay.
class instead of the minimum and maximum.
Yeah, that should be the minimum one, right? Like you can wait as long as you want, right? There is no harm. But yeah, activate. So it's basically like you are trying to open a new row on the same bank, and what is the minimum time you have to wait before opening a new row? That defines the minimum time, right? There is no harm in maximizing the time. Yeah, sure. Okay.
How it is scheduled with the cycles,
Okay.
you would have given the minimum. Because here we don't know whether, because we are getting the request later,
Mm-hmm.
we are getting this high activate to pre-charge, or is it because that this is the limitation?
Oh, no. So this is actually a snapshot of the events what you have. The question says that this is a snapshot of the request buffer. So it's not like that the requests are coming one by one. So the question you said, that's completely valid. If like, how do you know that, okay, this request actually came later, so that's why we actually issued this thing later, right? That's what you asked. But this question actually said that this is the snapshot of the request buffer at once, when you actually started seeing this. So your request buffer showed a state like this, and then you probe the command bus. That's what it says, that you probe the command bus, and you saw that, okay, this is the sequence of commands the DM command controller actually issued. Make sense?
What you're saying that it's like at one point of time we are getting this many requests to the same.
Yeah, no. So this means that when we actually started formulating, seeing this behavior, before this behavior, you already have this many requests inside your DRAM buffer, request buffer.
So from the scheduler point of view, it's like
Right?
at a time,
At a time, you have this thing. Now you just want to access this request one by one.
and what does that point say? For example, if there are requests A and B in the request buffer,
Mm-hmm.
A is the oldest request and two requests are two different banks,
Okay,
the
yeah,
memory controller does not issue an activate command to the bank B.
that's right.
It's going to access the request. So what does this mean here?
Here, okay. So, okay, that means this thing. So let's say this is the access, and the second access actually goes to a different bank, right? So instead of, if you don't know this criteria, that memory controller actually doesn't issue any, so there is no harm in issuing the command sequence for this second access, as long as the command sequence for first access is going on, right? Because the second access is actually going to a different bank. In a real life scenario, this could have actually exploit the bank level parallelism, right? Exactly. So then it says that, okay, unless the entire command sequence for the first access ends, you cannot simply issue any command sequence for the second access. That gives you a deterministic behavior, how you can actually categorize this access sequence for the particular request.
So if we have like multiple bank, multiple requests to a different bank,
Okay.
then in that case, this
It's just a,
level will, the scheduling will be different. In that case, if we are calculating the
mhm.
then it will be even higher, right? Because in that case, what we are doing, unless the first, according to
Okay.
this thing is completed, we can't send a request for other banks.
I see. I see your point. So you are saying, okay, it might get serialized just because of that reason.
So it might add
Okay.
cycles, and the things we are calculating for activated features might not be
The lowest one. Okay.
So if there are like after bank one, we are scheduling bank one,
Mm-hmm.
but we have access to a different row, then calculating.
Does make sense. Okay. So I would suggest, okay, this question is kind of going towards a straightforward notion of, let's say, categorizing the command sequences to map which access request it's actually serving. Okay. So now you can think of it like this. So cycle 11, and then there is nothing happening between cycle 11 and 21. So that means if all of these accesses are actually happened all at once, then there is some timing constraint which is hampering this thing to go forward. Make sense? So that's how we are calculating. Okay, then 6 to 21 is the minimum. You have to wait, and then you have to go on. Okay? So then 6 to 21, if you want to verify this with something else, you can also see that, okay, this timing constraint actually holds for other remaining access also. So, okay, the second one is precharge, third one is precharge to activate latency. Okay, now see. So, yeah, precharge to activate is straightforward. So, precharge to activate, and then precharge to activate. In all three cases, both these three pairs actually followed by 6 cycles, right? So, that means it has to be 6 cycles, which is equivalent to 12 nanoseconds. Make sense? Okay. Now, a little bit trickier question. So, what is the row size in bytes? And explain your answer. So, okay, to approach this question, I would say that you should first think of, let's say, a row buffer hit would actually give you an idea how big is the row buffer, and a row buffer miss will also give you an idea how big is your row buffer. Make sense? So, first approach would be to first figure out which accesses are actually going to the same bank. So that gives you the first access, the third access, and the last access. This is one candidate, these 3. Make sense? And these 2 are the another candidate. You can extract your information from these accesses. Does it make sense? Okay. Now let's see how big is the row buffer, right? So let's see the first sequence of accesses. So 4C80 and then 4EC0, these 2, and the last one 4E80. Okay? So let's see. 4C80 actually serviced by these 3 command sequence. The next one, the 4EC0, is serviced by these 3 command sequence. Now, if 4EC0 is actually getting serviced by precharge, so that means 4C80 and 4EC0 are not on the same row. That's one hint. Second hint, 4E80, this guy, and 4EC0, the last access to the same bank, it's also getting followed by the same precharge. So that means these 2 are also not on the same bank, same row. Does that make sense? Okay. Now we see that, okay, okay. So these 2, these two are basically 800 and 803F. So let's see. Oh, am I making some mistake? No, okay. So 800 is this guy, and 803F is this guy. So now if you see the axis number, this axis, 803F, last by 1. So last but 1, this axis is actually just a read sequence. So that means it's actually hit in the row buffer, right? So these actually gives us an idea that, okay, for 8000 and 803F, these two accesses belong to the same row, but the minimum one is basically 4E80 and 4EC0 actually belong to the different line. Now, what's the minimum size then? Like, which size of the row buffer will actually satisfy both of these constraints, right? So let's see. If we just decode the last two hexadecimal bytes, it's basically 0000. This is 1, and this sequence would be 0011, 1111. So that gives us this boundary, right? Okay. Now another one would be 0. Wait. This is what? 0800. Okay. So 1000, 0000, and C is this. Can you see the, like, can you identify the boundary of the row buffer? So it basically says that, okay, if these two address values are belonging to the same row, but these two address values are belonging to the different row, so that means your row size would have at least these many bytes inside a row. How many bytes of that? So you have 6 bits of addresses, 6 bits translates, so this is an byte addressable memory, 6 bits translates to 64 byte. Make sense? So that means your row buffer size would be of 64 byte. Is it clear? Okay. Okay, now let's go to the second question. Third question basically. Okay, so let's read the question. What is the status of the bank prior to the execution of any of the above requests? So these are the request sequence. Before this request sequence even happened to the DRAM, what is the state of the DRAM? It's asking for that question, okay? So in other words, which rows from which banks were open immediately prior to issuing the DRAM commands listed above? Fill in the table with below indicating whether the bank has an open row. If there is an open row, specify its addresses. If there is not enough information, just simply say unknown, okay? Let's see. So now, let's say open and closed. So your accesses to the access sequence that you are actually generating for a request will give you the information of the prior state of that bank. Does it make sense? Okay. So now let's see. So bank 0. So which access actually went to bank 0? This is the one which went to bank 0. The second access. What's the second access command sequence? Second access command sequence is this one. That's just a read. That indicates there is an already same row which is happening on the same bank, right? So that means, okay, the first question is open or closed. It's definitely open. That's why you actually hit that row. Make sense? Okay. Let's see now, so which row address is then open? Now, if you see this, so you have 16 bits of addresses. You know last 6 bits are basically the row address. So that means if you simply chop it off, so these 6 bits are actually going for the row offset. These 2 bits are actually going for the bank number. The remaining 8 bits is basically giving you the, am I right? Yeah. It's giving you the row number, right? So now if you simply calculate this, so let's say bank 0. So bank 0 means this axis is what? 0140. So 0001, 0001. Sorry? Oh, I'm sorry. Okay. So 4 means 0, 1, 0, 0, and 0, 0, 0, 0. Right? So if we truncate this, this is the 8-bit sequence you are left of. So this is 0, and this is what? This is 5. So that means 0, and that's 5. Does that make sense? Is it clear? Yeah.
Is it not also acceptable to write the memory address of the first addressable?
Well, yes. Okay, you're right. I think so. Yeah. So then it should be then it should be 0, 0, 0, 0, 0, 0, 0, 1. You know how to do this. So it's basically this is the first address, basically. Yeah. This is the first address. Does it make sense? But this is how you should actually approach the question. Like, the open row address would be the first row address, I guess. This portion will be anyway 0 for the first address. Make sense? Okay. Now let's go to the second bank. Okay, bank 1. So which accesses are actually happening to bank 1? Bank 1, these 3 accesses, right? The first access to the bank 1 is 4C80. 4C80, the first access started with the pre-charge thing. So that means, yes, this is open. Now, which one was before? Before this thing? Exactly. So we don't know this. Make sense? Okay. Let's go to bank 2. Now bank 2, this is the one. So this is the fourth axis. So let's say fourth axis is this one. Fourth axis basically says that activate and read. On what condition we have activate and read? We have a closed row, right? So that means bank 2 is already closed, and then there is nothing open here. Okay, fine. Now let's go to bank 3. Bank 3, the only access to bank 3 is this guy, the third last. Third last is this guy. So this is actually just a read command. So that means whatever you are accessing, it's hitting the row. You know how to, then this is definitely open, and using the same tactics, we can actually get the address of the open row. Make sense? Okay. Now comes the trickiest part of the question. So, okay, this question basically talks about the TLDRAM architecture. You probably have gone through the TLDRAM architecture, right? So it basically says that to improve the performance, you decide to implement the tiered latency DRAM. Now, assume that the bank consists of a single subarray. With TLDRAM, an entire bank is divided into a near segment and the fast segment. When accessing a row to the near segment, the activate to read latency reduces by 2 cycles, and the activate to pre-charge latency reduces by 5 cycles. Whereas when you're accessing the fast segment, activate to read latency increases by 1, and activate to pre-charge latency increases by 2. Fine. Now, this also says that, okay, let's just consider the near segment have the smaller row IDs. Just the first row ID basically belongs to the near segment, and the fast segment will have the higher row IDs. So basically 0 to n-1 belongs to the near segment row IDs, and n to m-1 is the fast segment rows. Okay? Now the question is, if the above DRAM commands are issued 5 cycles faster than the TLDRAM, faster with TLDRAM as compared to the baseline, so that means it basically says that it previously it ended in 52. Now what if it actually ends in 47? And then the question is, if it actually ends 5 cycles faster, then how many rows you have in the near segment? That's kind of a very neat reverse engineering. Okay? So let's start with let's say how to approach this problem in the beginning. So you have the activate to read latency and the activate to pre-charge latency. So it has something to do with the activate commands and how far the read and the pre-charge commands are apart from the activate. So let's target the activate first, and let's see which rows it's actually using, which bank it's actually using. Okay? So I'm going to write this again for this thing. Okay. Okay. Now let's see. Can I show this side by side? Yeah, that's possible. Okay. Okay. So now if we see, so let's say this is a precharge activate and the read command, right? So let's see this activate is happening to which bank and which row. Okay. So this activate is definitely for this guy, right? So this is bank number 1 and row number. Yeah, we need to calculate the row. I guess I have the row calculated somewhere. Okay, so this is row number 50, just for fasting. Okay, so this is just a read command for the second guy. So let's not consider that for now, because these guys are anyway not creating any activity request, so we might not consider it for now. Okay, so let's see. The third access also comes with the 3 issue sequence: activate, where precharge, activate, and read. So let's see. This guy is also to bank 1. This is row 59. I know this. Okay. So now this is an activate to read. This guy is for bank 2. And this is for row what? I believe it's 0. Yeah. This guy is again a hit, so we are not considering it for now. This guy is again a hit. We are not considering it for now. This guy is another guy which has an activate, so let's see. This is bank 1. This is row 58. Okay? Now what we need to see is basically we know what information. We know what is the latency sensitivity of the fast segment and the near segment. That's one thing. That's one information we know. And the second thing we know that, okay, these are the accesses which generated an activate request, and these accesses are actually happening to this bank and this row. Okay? Just by seeing this, you can probably get an idea that it might be somewhere between 58 or 59 or maybe 50. That's just a hunch. Okay? Now, let's start. I would say I would approach like this. So let's start with saying that, okay, row 50 is something we are considering to be a near segment. And let's say 59 and 58, both of them to be a fast segment. And let's see how the command sequence looks like. What the timing parameter actually looks like. If it doesn't match, we'll go back and we'll say that, okay, let's make 58 also as a part of near segment, not a fast segment. Okay? If it doesn't match also, then we'll go back and consider that 559, consider it also as a near segment. Yeah. That's what this line says, that, okay, you can consider 0 to n-1, the first few rows to be the near segment, and the remaining rows to be the fast segment. Make sense? Okay. Now, let's see. So if we consider, let's say, can I show this side by side? Let's say, okay, let's show this like this. It's visible? Okay. So if we consider, let's say, 50 to be the near segment, and 58 and 59 to be the fast segment. So basically 0 and 50 goes to the near segment, and 58 and 59 goes to the fast segment. Okay? Let's start with this one. So what we have the changes in the activate to read and the activate to precharge. So there is nothing for precharge to activate, right? Precharge to activate is same for everyone, right? So let's see. 0, 6. That's like the normal sequence. Okay? Now activate to read. Activate to read is basically, it was before 4 cycles. Now you know that if it is near segment, then it will reduce by 2 cycles. So that means later on it will come as 8. Okay? So now let's see. This guy is just a normal read. So it can simply go on the next cycle. So that's 9. Maybe it's a better idea to put it like this. Okay. And then see, precharge. So then activate to precharge is one dependency. If we know that, okay, this row is a near segment, if we have considered that as a near segment, so that actually gives you a 5-cycle benefit of activate to precharge, right? So previously activate to precharge, so this activate to precharge was 15 cycles, now it actually becomes 10 cycles. Just stop me whenever you can get the flow. Sorry? Right. So the question is to get the boundary, right? We need to get the boundary. Now we should start from some place. Let's consider 50 as a boundary. So I'm considering 50 for now. I'm considering 50 as a boundary. So anything from row 0 to 50 actually falls to the near segment. Anything from 51 and upwards is basically fast segment. Okay. So near segment, any access to the near segment comes with two benefits: activate to precharge and activate to read. Some cycle savings. Okay. Anything on the fast segment, which I considered this one and this one, is coming with a penalty, some access penalty. Make sense? So right now I'm just trying to figure out whether my intuition is correct by getting the timeline. If my timeline doesn't match with this constraint that, okay, you have five cycle faster, then I will roll back and go and consider some other row to be the boundary. Does it make sense? Okay. So, and I'm just reconstructing my timeline based on these assumptions. Okay? So, okay. We are at here. So this is the precharge. Now, this is the precharge. So this precharge is happening to the same bank. This is correspond to this axis, happening to the same bank. But now you need to close this guy. That's the near segment we have considered. So we will actually get a 5 cycle benefit. So that means now, earlier what 6, and this was happening at 21 because you had to maintain a 15 cycle gap. Now you can actually get it done at 16. Does it make sense? Okay. So now if you can get it done at 16, then precharge to activate, it's always same. There is no benefit in TLDRAM. So this timeline actually went to 22. That's 6 cycles, right? And then activate to read. Now consider this. So currently now you are at R59. R59 is a fast segment. So your activate to read will actually get penalized by how many cycles? Activate to read is increasing by 1 cycle. Make sense? So now your activate to read, previously it was at 4 cycle latency. Now you had to charge 5 cycle. So now this thing will actually come to 27. Yeah, go ahead. Right. Precharge to activate.
Yeah, we precharge the row 50.
Right.
Then we activate the row 59. But there are different tiers.
Yes. We don't actually have any benefits on the, at least according to the description, we don't have any benefits for precharge to activate.
And if we did, for example, hypothetically have it for our segment, for example, but this was precharged in the near segment and in the power segment.
No. Then it will be mentioned clearly that what. So if you're precharging a near segment and then activating a fast segment, all like that. Make sense? Exactly. All those combinations will be there. Make sense? Okay. Now let's move on. So this is the read request. So we have actually done. Okay, the read request is done. Now let's see. This is the activate request. This is the fourth request. Fourth request is going to bank 2, which is completely independent. So we can simply issue it on 28. I'm so sorry. Okay. So this is happening at 28. Okay. Now this is another activate, right? So we have considered that this R0 actually falls into the near segment. So activate to read is reducing by 2. So that means it's actually coming, this 36 is coming to 30. Make sense? Okay. Now let's see. Now this read is completely independent. So this can go and 31. Okay. And let's see. This is another read which is also happening on the same 6 means. Whoa. Access number 6 means this. This is the second 2. So this is happening at 32. Okay. Now let's see. This is a precharge. So this precharge will actually happening on the bank 1. Okay. So bank 1. Previously we have access bank 1 in the access number 3, request number 3. right? So this activate actually happened in 22, right? So now we need to check the activate to pre-charge latency. So there is a constraint. We have mentioned the constraint, right? So now when we have considered that, okay, row 59 was in a fast segment, so activate to pre-charge latency will get increased by activate to pre-charge by 2 cycles. So which it was as 15 cycles, now it will become a 17 cycle. Does it make sense? Right. So then we are just simply charging a 17 cycles for this guy, so that comes to 49. Am I right? Oh, sorry. Yeah, I think so. Okay. So now see. Now let's see. Okay. Now pre-charge to activate, it's 6 cycles. Okay. So I'm already passing. Did I do something wrong? Which one?
You added 17 to 32,
Which one?
You added your activated pre-charge latency to...
Oh, I'm sorry. I'm so sorry. Okay. So this should be 22 to 17, right? This one is 22. So 22 plus 17 should be... Okay? Yeah, I actually added from 32. So this should be 22 plus 17, 39. Does it make sense? Okay. Oh, thank God. Okay. So this is 39. And then, so pre-charge to activate is basically then 6 cycles more. That's like 4. Let me just put it this way. This is 45. Now activate to read. Now the activate to read, if this R58 actually, so we started with R58 as a fast segment, right? If this guy is a fast segment, that means activate to read, which used to be like 4 cycles, it has to be now 5 cycles, but you know that 5 cycles will overshoot. Then let's just consider this guy to be near segment. If we consider this guy to be near segment, that gives you 2 cycles benefit. So that means you can actually get it done by 47 cycles, which is like 52. Everything matches, you're happy. That's it. Okay? So I would say the approach would be just to, like, when you know that, okay, this is 50, 59, and 58, you know, consider some boundary, go with the timeline. If it doesn't match, then consider another boundary. Just like a normal search or binary search, whichever works for you. Yeah, go ahead.
Would it be possible to get a problem where the boundary is somewhere in the middle, like 80,
Mm-hmm.
and then your segment, we have an idea it's somewhere in the middle. If 85
Okay.
was the far segment for us,
Okay.
figure out that's the solution, and
Okay.
50 is the near segment.
Okay.
We technically can't know the boundary.
I see. No, so
Will you tell us that you have to give you a number, or you have to give an upper bound or lower bound?
okay. So if I would say the question would be deterministically answerable. If it is not deterministically answerable, then we are expecting some bounds. If it is not, then we are expecting a correct number. For this case, let's say you know for sure that, okay, if you consider 58 to be on that side, on the fast segment side, you are not matching the timeline. So that means 58 has to be on the near segment. And then you know that, okay, there is another guy with 59. So that means 0 to 58, 59 rows are actually in the near segment. But what if you don't have 59? Then you don't know actually the boundary, right? Then we are expecting not an exact answer, but as a bound. Make sense? At least, yeah. But for this question, it's completely definite that 58 is the boundary. Make sense? Okay, fine. Yeah, that ends my session. So, yeah. Do you have any other questions on this front? It's fine. Okay. So who is the next guy?
Can I start? Yes. Let's start with some new Warhammer problems. Yes, here, we should have thought about, what and how we consider when we develop the Warhammer mitigations. So the problem, let's read the problem. So one researcher rigorously investigated the relationship between the DRAM refresh rate and Warhammer introduced errors using real DRAM modules from 3 major memory manufacturers, and they used the most Warhammer vulnerable modules in each DRAM manufacturer. So, we can this graph is the worst case scenarios. So very conservative manner. And as shown in this figure, we can achieve an effectively zero probability of Warhammer-induced errors when we reduce the refresh interval to 8 milliseconds. So here is 16 millisecond, and before we reduce the refresh interval to 8 milliseconds, the errors of all modules are close to zero. So this is because the probability of Warhammer-induced error becomes less than that of a random DRAM circuit fault. Okay, and based on this, as a leading computer architect of a company, you are asked to design an efficient Warhammer mitigation technique. But your junior engineer suggests a very naive, but an immediate mitigation technique which reduces the refresh interval from the default value 16.4 millisecond to 8 millisecond. And this is very straightforward that the bank utilization and the energy consumption will increase linearly increase along the number of refresh requests we should perform in a same time interval. So E and U is linearly increased for number of number of refreshes, and if we reduce the refresh interval, we increase this. So we can easily know the energy consumption and the bank utilization should be increased 8 times, both. Make sense? And the next question is the feasibility of this approach. Fortunately, so the recent DRAM manufacturer successfully released a higher capacity version of the same DRAM module. And you figured out that with the rigorous reverse engineering, they only double the number of rows in a bank and the number of banks in a module without changing any other aspects. So in this case, in this question, asking how the bank utilization will increase along these changes, and if the number of banks and number of rows per bank increase 4 times, then how it should be changed. So with just the 2x increase, it is still applicable. And so here the current bank utilization is 0.05%. So in our calculation, when it decreased the refresh interval to 8 milliseconds, the bank utilization increased 8 times. Here is some fake information, right? So the bank utilization does not affect it to increase of the number of banks in a module. So we just multiply 2, which means double the number of rows in a bank. And this is 80%. And so this is possible. So in terms of Warhammer protection, because we can refresh every rows within every 8 milliseconds, so we can protect against the Warhammer attacks. But it is quite impractical because the most of bank utilization is consumed to the refresh. And if the number of rows and number of banks increases to 4x, and it is impossible to protect. Actually, it is impossible to reduce the refresh interval to 8 milliseconds because bank utilization becomes larger than 1. It means that even though we spend all the time for refreshes, we cannot refresh every rows in a module. And it means we cannot apply this approach if the number of rows and number of banks and number of rows increase to 4x. Okay, so this approach, this reducing refresh interval is not feasible when DRAM scales out. We should think about another approach. So due to significant overhead of reducing the refresh interval, you can decide to find another Rohammer mitigation technique with lower overhead. So the junior engineer proposed another technique which is counter-based. So in this approach, the memory controller maintains a counter for each row R, which increments when an adjacent row is activated. So note that there can be some multiple approaches using counter to mitigate row hammer effect. For example, we can count the number of activation of a row, and if it exceeds the threshold value, we can activate the adjacent rows of the activated row, right? But here, they did not choose that approach, but instead they count the adjacent rows activation, and if it exceeds the threshold value, it refresh the victim row, potential victim row. So there are many pros and cons for each approaches. Okay. So the question is, so here are a bunch of information about your DRAM modules for now. So here is interface generation and cost latency and TRCD, a bunch of information. And the question is asking, are the given specification enough to implement the proposed approach? And I think it is quite open question, but this question is asking the essential information to implement this techniques. So what I intended is we should know if we do something with about adjacent row, we should know where is the adjacent rows, right? But as we covered in our classes, a DRAM manufacturer does not open it. It is normally confidential. So we should know the existing mapping between row addresses and physical rows. In this case, Anyway, suppose that all the necessary specification, it means the exact mapping between the row address and physical rows for implementing the proposed approaches are known, and calculate the maximum value of T. So the threshold value that can guarantee the same level of security against the row hammer attacks over when adopting 8 millisecond refresh intervals. The reducing the refresh interval means that it limits the number of activation within the consecutive refresh, right? So the maximum we can, if we reduce the refresh interval, we can limit the number of activations, number of hammering, because the activation, the hammering method is now activation. We can limit the maximum number of activations. So actually, to calculate this very optimally, we should know. We better to know the possible number of possible activations within 8 milliseconds. But in theory, we can the maximum bound of the number of activations in 8 milliseconds with this low cycle latency, which is the sum of TRAS plus TRP. And so it means total, about 65,000 activations can be possible in single 8 milliseconds. So if we set the threshold value as this value, then we can at least guarantee the same level of security against the raw hammer attack over with the 8 millisecond refresh intervals. Make sense? And so the next question is asking the number of bits required for maintaining counters in each memory controller, and it's very easy actually. With B, let B is the number of bits. We can maintain these many informations, and so it should be larger than T, and definitely we need to calculate the maximum value. So minimum value of this. And we can simply know. With this some logarithm method, and this T is 18. So so for more correct more correct equation inequality is this. And with this value, we can simply calculate the number of bits required for the counters. And it can be increased 36 millibits if the number of rows and number of banks are doubled. Okay. So the reason why we use the maximum threshold value is to minimize the performance over it. So this question asking the goal of that we use the maximum value of maximum threshold value. So we can reduce the size of counter in each memory controller if we use a smaller value T. For example, if we use just a threshold value as 1, then the size of counters definitely should be increased a lot, but we need to refresh adjacent row whenever we activate our row. Twice or something. So the performance and energy overhead from unnecessary activation or refreshes is the cost of using a smaller threshold values. And the final question, you recall para, which is proposed in the first Rohammer paper. And here is some description of how para works. And I suppose you are already aware of it. So the key question is, we know the error for para. So error rate of para experiencing sorry for that. We know the probability for para to experience an error in 16.4 millisecond, which is very small. And let this as what? P64 millisecond. When the parameter, the probability parameter in para technique is just 0.001. And this is the worst operating condition. And the question is asking, how we can estimate the probability of experiencing an error in 1 year based on this value. So the problem. So this is the probability of experiencing an error for 64 milliseconds, and the question is to get this, which is the probability of experiencing an error for para in a year. Then we can consider a year as a sequence of independent 16.4 millisecond time intervals, and the number of 16.4 millisecond time intervals like this. Let's say this is this is m, and we can the number of errors in a year can be modeled as a random variable which follows a binomial distribution. With the parameters n is the number of 16.4 milliseconds time interval, and the probability is this value. And therefore, if the probability that at least one error occurs in a year can be calculated, the variable x, the probability of that variable x is equal or larger than 1, larger than or equal to 1. And this is because x is discrete value, we can simply know is like this. And in binomial distribution, the probability of the event never occurs is simply just multiply n times, and the final answer should be like this. And this can be, fortunately, this can be calculated with the calculator in your PC maybe. So, but it should be fine. Just leave this form in exam or homework as well. But and definitely if you use some approximation or some inequality, for example, Markov inequality, because this variable x should be this variable x, and the probability should be larger than positive value. Then we can use Markov inequality to bound the maximum value, and this binomial distribution with very large trials and very small probability, then we can approximate the distribution to Poisson distributions. So if you use that and refer to that reasoning, then it should not a problem in this question. You will get all the credit. Okay, any questions?
Okay. So this is a very interesting question, hopefully. and it's related to the lecture number 5 about accelerating genome analysis. And in this question, you are asked to solve 3 parts about finding the edit distance between 2 strings. So how many of you still remember this lecture? Okay, very good. All right, so edit distance is the minimum number of edit operations that you need to do so that one of the sequences will be similar to the other one. So those edit operations are 3 types, can be substitution, deletion, or insertion. And basically, you could follow the dynamic programming algorithm where you design it yourself or you solve it, you calculate it for each of those 2 sequences. Or you could, if you are smart enough, trying to find the number of operations that you need to do so that one of those 2 sequences will be similar or exactly typical to the next one. So let's see this example. You have moon tag and donut tag. Is that correct? Okay. So apparently, you have the tag part is common between the 2 sequences. So that gives you 3 matches. And you have another 7 characters that don't exactly match. So you have the S, R, and so on. So anyway, so for those kind of questions, you need to start from the very first character, and you move all the way until the end, okay? So if you try to do this way, that will give you some incorrect answer. And you need to note that, though you might find a way that you could make this sequence similar to the other one, but might not be the minimum, and that will lead to a wrong answer, okay? So you have to be very careful about those. And that's why we use dynamic programming algorithm to solve such kind of questions, so that we can enumerate all kind of prefixes. Oops, it's too late. Okay, can everyone see it? Okay. Okay, so in dynamic programming algorithms, we're trying to enumerate all prefixes and see which one gives you the minimum number of edit operations. So how we do it, let's try again. So you have the... let's type it again, one tag. And let's start with the D. Does D match here? No. Does it match the next few characters? No. So probably this should be substitution, okay? Now this is one operation. Now we have the O. Does O match the corresponding next character in the second sequence? Yes. Okay, that's perfect. So we have an exact match here. And then we move to the N, which is exact match. And then, unfortunately, we have another N. Does it match? No. Does it match with the previous character? Yes. So apparently you have an alternative solution here where you could have an exact match here, right? So you could delete this N or the next N, right? Both of them correct, by the way. So you could do that. And now what's the next? It's E. Does E match the corresponding one, which is A? No. Does it match with the next one or the previous one or the few previous? No. Now, how few you should go? How far you should go? Probably if the 2 sequences are short, then you shouldn't move more than 2 or 3 steps around that. But sometimes we call it a banded edit distance, where we restrict the number of steps you could move forward or backward. And in this banded, we give you a threshold, 2 or 3. So that will restrict you moving how many steps right or left. Anyway, so and apparently here we have another deletion. By the way, if it is a deleted character from this sequence, it's same as if you insert it in the other sequence. So deletion or insertion, same answer, okay? Now what's next? So we have the R, same story. We need to delete it. And we have the S, and then we have the tag. So how many edit operations we did here? We did 5. five steps, 5 deletions from here. We have the 1, 2, and we have another 3 here. Or you could do 5 insertions to the other sequence. Okay? Any question? Yes? So if you are banded with some limited number of edits, then probably this exceeds the threshold that we set in advance, then probably you don't need to continue. Because anyway, what does mean banded is you have the dynamic programming table, right? You have some diagonals. So banded mean number of diagonals that are next to the main diagonal. So if you have the main diagonal, which is the one in the middle, now the banded mean if it is 3, then you are allowed to construct only 3 diagonals next to the main diagonal. Likewise, you can construct another 3 here. So probably if you have 5 edits, for example, then your computation need to be exceed this limit, which is the band you have, which is 3 and 3, plus the main diagonal, 7 diagonals you have. So you cannot compute it using this dynamic programming table if it is banded. Okay? So probably you need to stop computing after you exceed that threshold. Then you can say that those 2 sequences has an edit distance more than the threshold, which is 3 or 4. Okay? So now let's go to the second. So let's try with the S. S doesn't match, apparently. Does it match with the next? No. Next, no. So apparently we need to delete this character from here. Then we have the A, same story, no. Then we have the M. We need to delete it. So we don't need to delete it, actually. Here, maybe substitute it. It's more accurate. Why is that? Because we want to keep it the same length. Okay? So we have the S and then the tag. So if we substitute the S with the I, M with the E, A with the R, and S with the F, then it will be exactly match, right? So how many edit operations did we do here? So we said 4, right? Because we need to substitute these. Okay. Now, we need to have this compared with a null sequence of empty characters. So apparently either you add all of these characters to the second sequence or you deleted them from the other one. So how many operations do we need? Equal to the number of characters here. Okay? All right. Now, why we explain the lecture about edit distance or other metrics that we measure the similarity or the difference between 2 strings? So we need that in genome analysis, for example, to tell us how many differences between your genome and the other genome, which could be a reference or somebody else in your family, for example. So here's an example of how we do that. You are given those 5 reads, and at each read, we chop it into 3 k-mers. And for simplicity, I give you the delimiter here, which is underscore, that divide the k-mers of a single read. So k-mer, the k here is the length of this substring or subsequence. So here we have the k-mer length is 5, so k is 5. So how many k-mers we have per read? 3. So we said in the question that this is a hash-based read mapper. What does that mean? Meaning that the first step in read mapping or in genome analysis, the indexing part will be based on a hash table. Okay? This is what does mean hash-based read mapper. That's why you are given this hash table, and you are given a bunch of reads. You need to map those to the hash table and start extracting some locations from the reference genome. So we are going to use the very basics method of doing that without any filtering, without any advanced mechanism in the first part of the question, which is this. Can you see it? Okay. So here you are asked that how many times you are going to apply this edit distance function. So how we do that basically is picking the first k-mer from the first read and go to the hash table. Does that k-mer exist in the hash table? If yes, then we extract all the corresponding locations. And at each location, we apply or we perform the edit distance function. So we pick the first k-mer, which is A's, 5 A's, which is here. How many locations? We have 6 locations. So at each location, we are going to check one by one the edit distance between this read and the reference genome at this location. So starting from 10 all the way to the same length of this, which is 15. So we start from 10 to the position 35 or 25, sorry. And we do the same thing with the other locations. Okay? So we pick from the reference at this location and we compare it with the read for edit distance. Okay, so how many times we do that? So the first one here, how many times occurred? So 6 plus AACs, which is here 3 times, plus the 5Gs 3 times. And now the second read, 4 A's plus T, which is 2 times. And then double G, double C, T, which is 5 times, plus A's, again 6 times. Now the third one, AETs. So I'm going to do some cheating here and copy the answer because it's repeating itself, right? Do you want me to continue? You just need to count how many times you get the location basically for this. So let's have it here, 2 plus 0 plus 0, and then 3 plus 2 plus 5, and then 6 plus 5 plus 3, and that will give you 51 locations need to be examined for edit distance. Okay? Yeah.
I just wanted to say that when I did it, because you can call edit distance with not the same size of the string you put as input.
Uh-huh.
So I chose to put 5 characters as input and to only call the edit distance on the ones that you didn't know that they matched. So for each read, you only call edit distance twice, but with parameter of size 5.
Oh, wow. Okay. Why would you do that?
Because it was not specified. And it actually, it's quicker.
Okay. So basically, you already know from the hash table that the k-mer is exactly matched, right? So now the question, where to perform the edit distance. So you already know that those 5 characters exactly matching with the reference, right? Now, whether you go to the next few characters or the previous characters in relationship with this k-mer, right? Now, okay. Yeah, if you assume so, nobody can argue with you, right? Unless it's specified in the question. But that's interesting. Okay. So now the second part, trying to do some sort of smart way of doing the comparison between the strings. So they ask you to use adjacency filtering. Adjacency filtering means you need to relate the k-mers together coming from one read. So you don't need to perform a distance per each k-mer. So meaning that here the distance between, so to call a k-mer adjacent to the next one, the distance between 2 k-mers should be 0. This is how they define it here. You can see they said if the first k-mer happening at the location x, then the second one should be at x plus k, which is 5. So they should really be next to each other. The distance between the k-mers should be 0. Okay?
Why would you call it a distance if you know it's 0?
Yeah, you can consider it as Hamming distance, for example, or edit distance 0.
So why do you call it if you know that it's...
So this is just to simplify the question so that you don't need to calculate the distance and subtract the... For example, if we allow for 5 steps between 2 k-mers, then that's considering 0, 1, 2, 3, 4, and 5. So you need to deduct all those possible values from a location such that you're on safe side, right? So this will complicate the calculation for your side, right? So anyway, if you want to assume that there's a single step between the k-mers, here the assumption is not valid, right? Because it's already given the question that the step is 0. So you cannot assume something else. The distance between the two k-mers should be 0. But the answer is not 0. Let's see what the answer is. Okay, so how we solve this question? Again, exactly same way, but we need to relate the two k-mers together, or the three k-mers coming from the same read. How we do that? Let's go to the first read, first k-mer. Then the 5 A's. How many times happening here? 6 times. Okay, now we shouldn't stop and perform at the distance. We need to proceed to the second k-mer, which is 4 A's and C. How many times happening? 3 times. Okay, now which one of these locations is adjacent to these 6 locations? How we do that? Now the 15 is really next to the 10. Why is that? Because the k-mer size is 5. If the k-mer length is 4, then the distance between the two k-mers is 1, right? So meaning that this location is adjacent to the 10. Now 610 is not adjacent to any of those, right?
We don't see on
the... Oops. Okay. Yeah, thank you. So the 15 is adjacent to 10, right? You agree on that. And the 610 is not adjacent to any of these. Why is that? If you add 5 to any of those, won't give you any of these locations. So the same thing for 720 is apart from 710 by 10 steps. So this is not valid based on the definition given the question. Okay? So none of these valid. Now we are having only single location coming from this. Now it's based on the third k-mer. If it exists adjacent to these two, or at least to this AC, then we are going to perform at a distance here. Yeah, I know it's stupid to perform at a distance here. Why is that? Because it's already exactly matching the 3 k-mers. So now let's see the 5 G's here. The 20. Is 20 next to 15? Yes, given that the k-mer length is 5. So we are going to perform at a distance here once for this read. How about the others? 600, 700, they are not adjacent to 15. So we just ignore them. Now we do exactly the same thing. Let's repeat for the second read, for example. So we have the 4 A's and single T, which is here, and we have 2 locations, okay? Now let's go to the second one. 2 G's, 2 C's, this one. Now let's start from the first one. Is 55 adjacent to 50? Yes. And 620 is adjacent to 50? We should check the entire list, okay? We cannot ignore one of them, even if we check it before. This is very important. So the 620 is adjacent to 15? No. Is it adjacent to 615? Yes. So we have 2 locations now. Now we repeat the same thing for those, and luckily they are not adjacent. Okay. Should I repeat it? Okay. All right. So now the third k-mer from the second read, which is 5 A's. Now we said we have 2 adjacent k-mers at this location, but those are not adjacent. So we need to check one by one for all of them. 55 adjacent here. No, maybe here. No, this is backward. You could apply it if you want, if you assume so, like not considering always the forward path. You could follow the backward, right? And actually, we do it in real life. Why is that? Because we have the DNA strand, and we put it in the machine. The machine starts reading character by character, right? But we don't know whether we are reading from the first character or the last character, right? So we always do the mapping backward, forward, or forward, backward, okay? So if you assume so, it's okay. If you don't assume it, it's correct again. Because based on the definition, it should be in the forward direction. We always have the plus sign, okay? Okay, so we are comparing now 55 with this. No, it's too far, too far, too far. So this one No, we should ignore it. Now 620 is... Oops, sorry. So this is the third Kamer, right? And this is the second. So this should be an increment of this, right? Yeah. So this is correct. Yeah, it's good that we mention it because to know that there's a forward and backward direction. So anyway, this 60 is next to 55, so it's correct. So we should keep this potential mapping, let's call it. And now 620, we should look for 625 here, which is this one. So we have it there. So this is a correct match. Now here, 650, what's next should be 655. Do we have it here? No. Okay. Yeah, anyway, we shouldn't continue, right? Because they were not matched from the second Kamer. So we have only those two positions, which is, the first one was here, right? So we have 50 and 615, and from the second Kamer, 55, 620, and from here we have 60 and 6025. So we have two mappings for the second read. Now you can repeat this exactly the same steps. Do you want me to continue? How many of you want me to continue? Okay, good. So we have 2. Here we have 0, I guess. Here we have 1 and 1. So in total we have 5. 5 times we need to perform edit distance. So apparently this smart way of using adjacency filter, reducing the number of times need to perform edit distance, which is very expensive because quadratic time, from 51 times only to 5 times. So you can see a huge reduction in the execution time of this software. Yes. What do you mean comparing?
Since now we are applying edit distance to 15 characters instead of 5.
No, the edit distance here between 15 character, right? So the read length is 15, right? So this location of the Kamers, which is starting from 50 to here, 60 plus 5, which is the end of the Kamer. This is the start index of the Kamer. So you need to add 5. So again, this is 15. So the length of this, the length of this is 15 again, right? Similar to the length of the read. So you have from 50 to 65, this portion in the reference. The reference is 3 billion character, around that, 3.2. Okay? So we only go to the location 50 all the way to 65. And then we pick this string, we go to the read, and we compare them together. Now they are equal length. Okay. Okay. So now let's use another method. Yes?
I just still don't understand why you perform those 5 edit distance. You know that the distance is 0, right?
Yes, that's true. Okay. That's a good question. But again, we mentioned that the distance between the cameras is considered 0 for simplicity of the calculation, right? But if I consider it to be 1, for example, then you don't know whether this 1 is insertion, deletion, or substitution, unless you try edit distance algorithm. This is in case I allow for a distance between 2 Kamers to be 1, for example. But here, in this question, I ask you to keep the distance between the Kamers as 0. Okay? But that's true. Maybe we should try it. Let's have this question in the exam. Let's try the distance between the Kamers to be, for example, 5. Let's see. Okay? Yeah, that's a good point. So again, if you are not sure about any point in the exam, you need to assume it. Otherwise, you won't solve the question. Okay? But if the question asks you for something very strict, you cannot assume in this case. Right? Okay. Yeah, some people were like writing half page of assumption, which is invalid. That's not true. Yeah, you cannot just write whatever you have in your mind. It should be valid, should be logical, should be following the given points in the question. Okay? Yeah, we still have the third question, which is some smart people like you proposing another method, which called cheap K-mer selection. So now let's try and see whether that improved the execution time or the number of times we are executing this edit distance function or not. So let's go back to the read. So we have the read set, and the definition of cheap K-mer. Luckily, you got all those definitions, so you don't need to memorize them, right? So we defined already this method, and whatever new algorithm we propose in the exam will be defined. Okay, just you need to follow the definition. So it says you have a threshold, and whenever you have many locations, more than the threshold, you just ignore this K-mer, or you don't perform at the distance. Okay, as easy as this. And what's the threshold here? The threshold is set to be the threshold is set to be 4 here, and so now the question, do we need to apply this cheap K-mer selection on the solution we perform in B or A? Why? Do we mention something about it? Okay, it seems we didn't mention about it. So again, you can assume it here. So you can assume that I'm going to follow the adjacency filtering and applying the threshold together. That's true, it should be correct. Or I'm going to change step 3 here and apply the threshold, where here doesn't mean I have adjacency filtering, okay, which is here, the original question. Okay, so both of them is correct. So now we go here, we pick the first K-mer, here, and we go to the hash table, 5 A's, we got 6 locations, 6 hits. Now, my threshold is 4, so anything exceeding 4, not equal or greater, but exceeding 4, we are going to ignore it. So we ignore those 6. We could say that we will consider only 4 locations without ignoring the seed, meaning that I'm going to consider those 4 locations and ignoring those 2, for example. If you assume so, it's correct. Okay? Now we go to the second K-mer. It's less than 4, so we apply here for each location an edit distance algorithm. So you have 3 times and 0 time from the previous, if you assume so. And then you have 5 G's, which give you 3 locations, so you need to apply here 3 times edit distance. Now this is for the first read. You could do the same thing. Let's take, for example, the last one. So you have 5 A's, 6, the same thing applies here. It's up to you. You want to consider 6 location, or you want to consider no location, or 4 of them only. But you cannot consider 6 because the threshold is 4. So the second K-mer is 2 G's, 2 C's, 1 T. You got 5 locations. Same thing you could do to the 5 A's, where the threshold is 4, so you can consider the first 4 locations, or you ignore this one. And then the last K-mer here, it's 4 A's, 1 C. 4 A's here, so you got 3 locations. Sorry, on safe side, you can apply edit distance to 3 of them. Yes? Yes. Violating the question. Yes, that's true. That's true. Then our assumption is not valid. Okay? So you cannot, if there's 6 locations, you cannot consider 4 of them and ignore the rest of them, okay? So if it is exceeding, just ignore it. As simple as this, okay? So yeah, you can assume whenever it makes sense for you to solve it, but you have to be careful about what the question asks you to solve, okay? Any question? So we have Juan to solve the next question. I'm not sure. Yeah, let's see. Right, thank you.
I think we are essentially done already because it's only 4 minutes left. But I won't quickly comment on the next question that we were planning to solve, which is about memory computation or computation using memory. It's like using the ambit substrate that Professor Mutlu has explained in the lectures. This question is question 4.1 in your homework too, but it also was an exam question, midterm exam question, actually in fall 2017. I'm not going to read it completely, and actually I'm not going to solve it. I will essentially read the solution given the amount of time that we have. So in this question, what we are going to work with is with the bitmap indices, which is one of the benchmarks that is used in the ambit paper. You might remember it. And essentially here, what we have is a database, and we want to query this database to find a solution, or an answer to the question, how many unique users were active every week for the past W weeks? So the way that this information is represented in the database is by using individual bits. Each individual bit in a row identifies one particular user, and we are going to have all the bits corresponding to different weeks in different rows. That's essentially what the question says. We have to compare 2 possible implementations. One of them is CPU-based. The other one is ambit-based. In the case of the CPU-based, what we are said here is that we need to make very basic or simple assumptions on how to compute the throughput of this implementation, because this is a very memory-bound operation. The only thing that we are going to take into account is the memory bandwidth. So essentially, this will be the cost of bringing the data from memory to the CPU, and then this computation, which is very little one, it's essentially hidden by all this data movement. And in the case of the ambit-based implementation, we have an accumulation row and we have an operand row. So in the accumulation row, we are going to have the partial results until we go over all the weeks, and then we will have the final results for every single user here in the accumulation row. And to the operand row, we need to move the row corresponding to the week that we are evaluating. Another thing that we are set here is that we are given 2 latencies. The first one is TRC, which is the latency of a row clone operation, because whatever row representing the activeness in a single week, we will have to move it to the operand row. And then we have this T-AND, which is the latency of an AND operation, because in order to merge all the results from all the weeks for the different users, the operation that we do here is an AND, a bitwise AND. So first question is, what's the total number of DRAM rows that are occupied by U users and W weeks? So first thing to keep in mind, to take into account, is what's the size of the DRAM row. It is 8 kilobytes in this example. So in every row, what we have is 64K bits. So we can fit 64K users in every row. If the number of users is U, we will need all this number of rows to keep all the users for a single week, because we have W weeks to evaluate. This is a total number of rows. The calculation of the throughput is quite simple, as you will see. First of all, we are going to evaluate the throughput on the Ambit-based implementation. In order to calculate the throughput, what we do is essentially, because it's the throughput in users per unit of time, in users per second. So what we will have is a fraction. In the numerator, we will have U, which is the number of users. In the denominator, we will have the total time that we need to compute for these U users and W weeks, right? So this total time is going to be the total time for all the AND operations plus the final bit count that the question says that it's computed on the CPU, because Ambit doesn't include bit count operations. So if you look at this AND total, what we have here is exactly the number of rows that we need to operate on, which is the solution of part A, times the total latency for each of these rows, which is the latency of moving the row to the opener row plus the latency of ANDing the row with the accumulation row. And finally, for the bit count, the only thing that we need to do is moving the bits corresponding to the U users at a certain rate, and this rate is the bandwidth, which is X. So this gives us this amount of seconds. That was for the Ambit-based implementation. For the CPU-based implementation, computation is even simpler. Why is that? Because we only need to think about what's the amount of information that we need to move, all these bits, divided by 8, because it's number of bytes, divided by the total bandwidth, which is X bytes per second or gigabytes per second or whatever. Okay? And finally, last part, what's the maximum W for the CPU implementation to be faster than the Ambit-based implementation? It's very reasonable to ask ourselves this question. Why is that? Because Ambit essentially is going to be efficient if we are operating on entire rows, right? If we are operating only on very few users, let's say 5 users, it doesn't make sense to compute using the Ambit engine, right? It would be wasting a lot of energy and potential throughput there. So as you can see, what we do is comparing these two times TCPU and the total time for the Ambit implementation, which is on the right part of this equation, and from here we can obtain W, which is the maximum number of weeks, in this case, for which the CPU implementation will be faster. Okay? So this is all, it's 4:04. So the only thing to tell you is to wish you good luck for the exam next Thursday. You can use Moodle, as you know, to keep answering questions, about these questions that we solved today, the questions in the homework, and we will try to help you as much as possible. The exam, very briefly, the exam will start at 12. I mean, it's 12, right? So 12 to 3. So it will exactly start at 12. So please be here like 5 minutes before that, because, I mean, according to the catalog, the exam is 180 minutes, and that's exactly the total time that we have for usage of this room. Okay? Any question? Yes, it will be here. In this. Exactly like that. You can bring it. Yeah? Okay. I mean, what does it say? 5 A4 sheets? That's what you can bring. Okay? No calculators, that's for sure, and no other electronic devices. No, the part 4.2 is not covered, but you have the solution in the website already.
All of the other questions
Yeah, all of the other questions, I mean, no, we don't have obviously time to solve them. Essentially what we do when we prepare one of these discussion sessions is that we select questions that are interesting and we sort them in a way that, somehow in order of importance. So the remaining questions are somehow similar, related to the questions that we already solved. And
they can be found in the material that is already in the course, right? So like in the
yeah, all those questions, the solutions to all those questions are already released. Yes. Okay, thank you.